Welcome everyone. Today's video is about the time when I studied astronomy in college. One module was about making 4 astronomical experiments which could be performed easily. So with little equipment, any of you could do these as well. The tasks I did were about recording a partial solar eclipse, measuring the rotation of the Earth, projecting the daily arc of the Sun, and photoshooting star trails. Let's begin. The first task was long before I even had the module, and I did it out of sheer curiosity. Since solar eclipses are for each region a rare occasion, our university put up telescopes on the physics department so people could watch the eclipse in more detail. Wearing those special glasses works as well, of course. But since my parents' home was a few hours away and this was in the break between semesters, I wasn't around the college. So instead, I tried this out at home with a simple telescope from my childhood. But just to be sure, here are some visuals about what's going on. The moon gets in a line between Earth and Sun. It throws a shadow onto Earth, but the core shadow only covers a relatively small region. Outside of it, you can still see a lot of the Sun, and for this event, it's also just a partial solar eclipse. All over the world, you can find usually 1 or 2 total or annular solar eclipses per year. But while staying in just one region, they are certainly far rarer, appearing decades or centuries apart. With partial solar eclipses, you will have far more luck in your lifetime without traveling around. Anyway, I was at home and wanted to capture the event with my simple telescope. And using the cardboard wasn't planned, just a quick solution as something went wrong. And there are 2 main ways of watching the eclipse with details. Method 1 is putting a special filter foil onto the front to heavily reduce the incoming light and making it safe to look through. With the right setup, you can even record the image directly with a camera. Like my neighbor who came over and simply took a clear picture with his smartphone while my camera simply didn't work out. And since I noticed the error mid-eclipse, I had no time for an elaborate plan and quickly went for method 2. You aim the telescope at the Sun without the foil and put, for example, paper at the other end. The projection can be watched by several people and of course still be photographed. Word of caution. You know how you shouldn't look at the Sun for long with the naked eye and how you can use a magnifying glass to ignite glass and paper? Well, a telescope focuses light even better than that, so it's a terrible idea to just look at the Sun with it. Like, you just go blind. So never look through an unprotected telescope at the Sun. Also, this is not aluminium foil. Please don't try that out. Use a foil that's specifically made for solar observations. Overall, this is an interesting and fairly easy observation method and can also be used to study sunspots. But please read up on it before you try it out. The Earth's rotation does not last 24 hours. But it's close enough. And with the setup of the second task, you can even measure how many minutes we are off. For this, I went outside at 1 AM 3 nights in a row. In my college town was a mountain close by and I wandered up the slope for like 20 minutes to escape the city lights and get a better view to the south. I sat down next to one of the institutes of the university. For the setup, I brought a camera as well as a tripod. Chairs were already there, otherwise a camping stool would come in handy. But what's the plan here? You look at the direction and arc which the Sun takes during the day. For me the optimum was south, 40 degrees above the horizon. You want to find a bright star in that general area. But you also want that your view of the star gets blocked by some obstacles too, like it vanishes behind a building within the next 10 minutes. Since the position of the view is very important, using a tripod and camera while marking the position is very helpful. Once the star of choice hides behind the object, note the time and repeat this at least once. And yes, that's it. You just need the times of this happening for different days. I did this 3 nights in a row, always walking up there after 1 AM. And the times were 1:24, 1:20 and finally 1:16. Now what does that mean? That the Earth made a full rotation in 23 hours and 56 minutes and some additional seconds. Although the 24-hour thing isn't really wrong either. So what's up with that? After those 23 hours and 56 minutes, the Earth faces the same direction in space, hence we see the stars in the same direction. At that moment though, the Sun wouldn't be in the same position from our view, since the Earth revolves around the Sun. For example, when we start at high noon and wait 1 full rotation, then it's 11:56, and the Sun is slightly off to the east. But 4 minutes later she's at the correct position again. In other words, the 24 hours measure the time until the Sun made seemingly one rotation around us, which is slightly off from the Earth's rotation. By the way, without this rotation, the year would be one extremely long day, which you can witness both at the North and at the South Pole. And the movement from one day out of 365.25 days equals to 4 minutes out of the 24 hours. When you say that the Sun rises in the east and settles in the west, then you'd be wrong for the majority of the year, since it's only correct for 2 days. Most days it's more like northeast, east-northeast, southeast, and so on. So it works in a very vague way, but it still changes a lot across the year. Anyway, for the third task, I projected the path of the Sun during the summer solstice, which arguably wasn't the best time of the year to stay outside the whole day when you can't really deal with sunburn. And I stayed there for 12 hours and did little errands between taking pictures. At one point I had an appointment in the citizen office for something regarding my hometown, which by the way is a 4 hours journey apart, but that part was sadly a waste of time. While staying outside the whole day, I also met a few people who were wondering what I was doing there, or we just talked about astronomy in general. Like, what could we do in case of an asteroid heading for Earth, or thoughts on humans traveling to Mars. The method for this one isn't anything spectacular. Put some sort of staff vertically onto the ground and mark the endpoint of the shadow in regular intervals. It's similar to a sundial, just that both the angle and the length of the shadow are important. The biggest problem is fixating the staff while having a big and flat plane to project the shadow onto. And the bigger the staff, the larger the plane has to be. I also read the recommendation to put a hole into the object to mind finding the center point more precise, because the shadow of, let's say, a ball gets stretched depending on how low the Sun is currently, though the hole isn't visible at the right angle. I won't go deep into the explanation, since it's pretty much the same reason as to why we have seasons. The Earth's rotation axis is tilted, and it stays like that while we orbit the Sun. So depending on the time of year, the North Pole either points towards or away from the Sun. Whatever half is pointing towards it is experiencing summer. And there the Sun rises far higher above the horizon at noon, and it rises and settles in northeast and northwest, respectively, on the longest day. And in winter, everything is simply reversed. For the final part, I wanted to record one of those popular star trail photos where you can see the stars forming circles in the night sky. I did this in the garden of my parents, since I live in a village, which also tends to shut off the lights deep in the night. I read how to set up a camera for this and went outside with my girlfriend. The whole thing took half an hour and it was a quite comfortable summer night. There are different methods of doing this, but in any case, you need to collect the light of the stars for quite some time. The longer the photo session, the longer will be the arc of the stars. And after one full Earth rotation, which is around 23 hours and 56 minutes as we learned earlier, each star that doesn't settle below the horizon would form a full circle. I went for taking multiple photographs and meshing them together afterwards. With the right setup and equipment, you could also make this 30 minutes one continuous recording. But even when you just want to take single pictures, the light from the stars is so faint that you still need to record it for a little while to get an image. My photographs all went for 30 seconds each, and every minute I took the next shot. And then in the program, like Photoshop or GIMP, you combine the layers by adding the light value. And here's how the finished image looked like. You see individual bumps from each photograph and even see shooting stars that came by mid-shooting. You can even verify the length of the recording by measuring the arc. Not sure why you would want to do that, but I just find it neat. I won't add much on the side of the explanation. While we can witness constellations slowly changing their form over the centuries, for casual observations it's more like the stars are standing still, and the seeming movement is mostly due to the Earth's rotation. And since the Earth's rotational axis goes roughly through the North Star, we have just one visible star that seemingly stands still. On the southern hemisphere there's no visible star at that mirror point, but the stars seemingly still behave like they are rotating around the center. Was there anything new for you today, or a story or fact that you would like to share? Please write it all below, I would love to read it. But that's everything from my side for this video. Any interactions are always welcomed, and here are the places where you can find me. Have a great time, and I will see you around.